The answer is the attacker can learn both the length of M and which blocks in the message are equal. The attacker learns the length because the length of the ciphertext is actually equal to the length of M. The output for our encryption function is the same length as its input, so we know that these lengths are equal. This assumed that the file contents M were an even number of blocks, since we're dividing M into blocks. If it's not, we'll have to do something about that, and we'll get to that soon, but the solution to that is to add padding. The other issue, which is a more serious one in this case, is the attacker learns which blocks in M are equal. This might not sound like such a big problem if we're thinking of the blocks as 128 random bits. Maybe the probability that two blocks are equal is actually very low. We'll see later in this class it's not quite as low as you might guess. But the message is not random bits, right? The message of the file, if we're thinking of these as 8-bit characters, well, 128 bits is only 16 characters. If they're Unicode characters, well, then we have more than 1 byte per character. This could get down to a pretty small number of characters. There's certainly lots of sequences in many files that would be 16 characters long that could be repeated. So this is a pretty large amount of information to leak. We want to find a way to encrypt our file that doesn't do that. Ways of using ciphers like this are called modes of operation. The one that I just described is known as electronic codebook mode. And the reason for that is you can think of having a book that for each input message, 128 bits of input, there are 2 to the 128 minus 1 inputs, you would be able to look up the value of encrypting that message. So you could have a code book that gives you for each input the 128-bit output that corresponds to that input. And this would be a really big book. If we assume we could get about 10,000 entries on a page, and each page weighs 5 grams, well, this would be about 1.7 times 10 to the 32 kilograms to carry around. And that's just for one key. So it's certainly not practical to think of this as being a physical codebook today, but this is really the same thing that the early codebooks did. They just provided a one-to-one mapping between inputs and keys. And that's exactly how we're using AES here, is to provide that mapping. And we're using the same mapping every time we need to encrypt the same value, we're getting the same output. This is the problem that we mentioned earlier, that it doesn't hide repetition in the message. Another problem it has is that someone could scramble. An attacker could move blocks around, could replace blocks, could change things, and it would still decrypt to a perfectly valid message, just with the blocks in a different order. So those are problems with the electronic codebook mode. We're going to look at some alternatives that avoid some of those problems.